Hi there, welcome to my channel. In this video, I'm going to discuss about the solution for finding the minimum number of arrows to burst the balloons. Let's look at the problem description. There are some spherical balloons taped onto a flat wall that represents the XY plane. And the balloons are represented by the 2D integer array where each point is an array of two integers, that is the starting and ending point of the diameter of the balloon. And we can short the balloon directly vertically, and the balloon can be short if we shoot the arrow that falls between the point start and end point of the diameter. And also there is no limit to the number of arrows that can be shot. So given that array of points, we have to return the minimum number of arrows that must be shot to burst all the balloons. Let's take a look at the example 1. We are given 4 balloons that are represented by these 4 elements. So the expected output is 2. With 2 arrows, we can shot all these 4 balloons. So if we shoot the balloon at the point 6, these 2 balloons can be shot because these 2 balloons diameters are overlapping at a point 6. In fact, it is overlapping from the point 2 to 6. Okay. And if we shoot the arrow at a point 11, these 2 balloons can be shot. Okay. So these 2 balloons overlap starting from the point 10 to 12. So if we shoot not only 11, if we shoot between 10 and 12, these 2 balloons can be burst. So that's why the minimum number of arrows to burst all the balloons, all these 4 balloons, are 2 arrows. Okay. So in the case of example 2, none of these balloons diameter is overlapping. So the expected output is 4 arrows. Okay. The constraints are then the length of the points array is ranging from 1 to 100,000. And each element in that points array is of length 2. So there are 2 integers. And the value of the points in the x-axis is ranging from minus 2 to the power 31 to 2 to the power 31 minus 1. Let's look at the approach to solve this problem. So we are given this 4 points and the expected output is 2. So with 2 arrows, we can burst all these 4 balloons. So if we draw all these 4 points in the 2D plane, we can see there are some overlapping between the points. The first point is 10 to 16, and the second point is 2 to 8, and the third point is 1 to 6, and the fourth point is 7 to 12. So after drawing these points, we can see there are some region where we can see the overlaps between the points, and here and here. So in order to find the minimum number of arrows, we have to group the points which are all intersecting each other. For example, if you see the point 1, 6 is overlapping with 2, 8. So we can burst these 2 balloons if we shoot between the point 2 and 6. And if you want to include the third point, we cannot include, because in order to include a new point to the group, that new point should be partially within the previously formed intersecting region. So the intersection is from 2 to 6, but the third point is starting from 7, which is outside of that intersecting region. So we cannot include the third point. Instead, we form a separate group. So this is the first point in the second group, and when we see this point, it is having an intersection from 10 to 12. So these two balloons can be burst by shooting between 10 to 12. So totally there are two groups which are intersecting. Okay. So one thing we notice, if all the points are sorted based on the end point of the diameter. So first we have to sort the given points array based on the end point. This is the actual input and this is after sorting. Okay, so if you see 6 and then 8 and then 12 and then 16. Okay, so after sorting it will be easier to check whether the consecutive points are overlapping or not. That's what I have listed here. So basically we have to group the consecutive points that are all intersecting each other and count the number of such groups, then return it. So this problem can be solved using the two-pointer approach. And first we have to sort the input array based on the end of the balloon's diameter point, and then initialize the minimum arrow count to 1, because the constraint is the number of entries in the input array is at least 1, so we can initialize with 1, and then initialize the idx pointer to 1 and initialize the current pointer to 0. The current pointer is the first element of the group, the first element that was added to the group. Okay, so in this case when we begin, the zeroth element is the first element in the first group. Okay, then we traverse the rest of the array and check whether the starting point is within the end, the current's end point. Then we can include that point to the group, current group. Okay, so that's what we are checking. Is the start point of an element pointed by idx is greater than the end point of the current element, then we have to increment the minimum arrow count. Basically we are forming a new group and accounting that new group, and then assign the idx to the current value, because the current should always point to the first element added to the new group. Okay, so then we traverse the rest of the array, and at the end the min arrow count will have the minimum number of arrows to burst all the balloons. Let's look at the flow chart. Input for this procedure is an array of points. First we initialize the current pointer and then the idx pointer and the min arrow count variable. So the current is the first element added to the first group, and the idx is the element which is going to be processed next. Okay, so first thing we have to do is sort the input array based on the endpoint in ascending order. Okay, then in this loop we check whether we process all the elements or not in that array. If not, we go ahead and check whether is there an overlap between the points pointed by the current and the idx. If so, we proceed to process the next element, because the current element will be added to the current group. If there is no overlap, then we are going to form a new group. So we increment the minimum arrow count, and then we update the current pointer with the value idx. So in the new group, the element pointed by the idx is the first element, so that's why we are assigning it here. Then we keep processing until all the elements are processed. Once all the elements are processed, we come out and return the minimum arrow count. Let's move on to coding. First I define the start and end constant. Inside the find min arrow shorts function, I sort the input points array based on the end point. So it is easier to check the overlapping condition in the sorted array. Next, I initialize the first point variable. This always points to the first element added to the current group. So initially, the 0th element in the array is the first point. That is part of the first group. Next, I initialize the count variable. With the length of an array. Then I initialize the minimum arrow count to 1. Then I write the for loop, which traverses the array starting from index 1 to the end of an array. And each time I check whether the start point of the element pointed by the IDX is greater than the end point of the first element in the group. If so, there is no overlap between the first point and the current element, so we creating a new group, incrementing the minimum arrow count and then updating the first point to point to the current element. Then finally I return the minimum arrow count. Next, I'm going to run the test cases. All the tests passed. Next, I'm going to submit this program. Cool, this program is accepted. Next, I'm going to do the code walkthrough with sample input. Let's do the code walkthrough for this input. So the expected output for this is 2. So with 2 arrows, we can burst all these balloons. So in the find min arrow shorts function, first thing what we do is we sort that input array based on the end of the diameter, balloon's diameter. Okay, so this is the input. After sorting, all the points are in the ascending order of their end of the diameter, 6, 8, 12, 16. Okay, and we initialize the count variable to the length of that array, and the first point variable is pointing to the first element of the current group. So in this case, the 0th element is the first point of the first group, and the minimum arrow count variable is initialized with 0 because we already formed a group. So after sorting this, and then in the iteration 0, first point is pointing to the 0th element, the IDX is pointing to the first element. We compare whether there is an overlap between the element pointed by the IDX with the first point. If so, we add that to the group. Okay, so in this case 2 is less than the endpoint, so these two, this will be added to the group 1. So there is no change in the min arrow count and also the first point. Okay, so in the iteration 1, the IDX is 2 and the first point is still 1 comma 6, and when we compare, there is an overlap between these two. In this case there is no overlap because the starting point of the current element is greater than the end point of the first points. Okay, so we have to form a separate group, so that's what we are doing here. We increment the min arrow count, so the min arrow count becomes 2, and we update the first point with the value pointed by the IDX. So the first point of the new group will be 7 comma 2. Then in the iteration 2, the IDX points to 3 and the first point is 7 comma 12. So we check whether there is any overlap. Yes, there is an overlap between the first point and the element pointed by the IDX. 10 is less than the 12. So we include this to that second group and we are not updating anything. So then we come to the end of the array. So we break out of the loop and return the min arrow count. So with min arrow count is 2. That is an expected output. Next I'm going to do the time and space complexity analysis for this solution. Let's do the time complexity analysis for this input. So first what we are doing, we are sorting the input array. So the time complexity for that sorting is n log n. Okay, then how many times this operation is performed? For this input it is starting from 1 to 3, so 3 times this loop runs. So for 4 elements, this operation is done 3 times. For n elements, this operation is done n minus 1 times. So the total time complexity is order of n log n plus order of n minus 1. So we take the dominating term. So the overall time complexity for this algorithm is order of n log n. So with respect to the space complexity is order of 1 because we are not allocating any additional space. We just use only few variables which are independent of the input size. So the space complexity is order of 1. Thanks for watching this video. Have a great day.